Now that we know about neurons in their resting state, we will learn about how they begin to prepare for firing. In other words, depolarizing the cell. And that's what we call postsynaptic potentials. As you know, the neural language is basically composed of electrochemical impulses. That is to say that when neurons fire, there is a chemical and an electrical process that is occurring. When we generate and conduce postsynaptic potentials, we're talking about the secretion of converting an electrical impulse into a chemical impulse and vice versa, creating a chain reaction throughout the nervous system. The chemicals that we speak of here are called neurotransmitters. You may remember this from your general psych class. These are serotonin, dopamine, GABA, norepinephrine, and many others. These are chemicals that influence our behavior, our thought processes, our actions, and our emotions. In order to understand postsynaptic potentials, I would like us to break up the word postsynaptic first. So when we're talking about post, we're talking about the after, and then synaptic, we're talking about the synapse. You may remember that the space between each neuron is what we call a synapse. So what we're referring to here is that after a neuron has fired, there is a potential that it has on the neuron across that space that we call the synapse. And so we'll be looking at the generation and conduction of postsynaptic potentials, PSPs. Please note that neurotransmitters are these chemical messengers that would bind to a postsynaptic receptor. And the receptor would be on the receiving neuron. It takes a neuron to send it, and then there's a take neuron to receive it. And so these chemicals bind to the receiving neuron, and they would then cause electrical changes. Remember just a few slides back in the previous module, we talked about how, for the most part, in a resting cell, there is a negative charge. This would mean that the cell is polarized. When we depolarize a cell, we would be decreasing the resting membrane potential. That means we'd be making it less negative. Instead of being negative 70 millivolts, it would now be negative 60 millivolts. And this would bring about a change, the beginning of a depolarization of the cell. This is what we call excitatory postsynaptic potentials, or for short EPSP. Please note that this increases the likelihood that a neuron will fire. The opposite of that is what we call inhibitory postsynaptic potentials, or IPSPs. This would be the same as hyperpolarizing a cell, which would mean that instead of leaving it at negative 70 millivolts, we would be increasing the negativity from, say, negative 70 to about negative 75 millivolts or even more. By hyperpolarizing the cell, we decrease the likelihood that a neuron will fire. Although this will be repeated later, please note that both IPSP and EPSPs are considered graded responses. This basically means that the amplitude of the EPSP or IPSP, meaning how high it is, how strong it is proportional to the intensity of the signals that elicit them. In other words, a weak signal would elicit a very small postsynaptic potential, whereas a strong signal would elicit large ones. Think of the sensation in your mouth after eating perhaps tajín, which is a powdered chili sold in a lot of Mexican stores. And this, even though it's chili, it's not spicy at all. So that would be a rather weak signal that would not elicit a strong sensation, burning sensation in your mouth. But if we compare that to biting habanero chili, that would then generate a stronger response because the signal would be intense. Postsynaptic potentials can in fact be integrated and eventually generate a larger response, which is what we would call an action potential. Action potentials, or APs, are massive but momentary reversal of the membrane potential from about negative 70 to positive 50 millivolts. That is to say that the neuron would have lost its polarization completely and it would now be a positive cell. That means that when the cell is positive, that means it cannot fire. It doesn't carry a charge. When it carries a charge, it's at a negative state, and that does have the possibility of firing. In order for an action potential to be generated, please note that one EPSP, which is what would make the cell less negative, would not suffice typically to cause a neuron to fire. A summation of multiple EPSPs, summation and addition, a compilation of several EPSPs, are needed in order to generate an AP. Please note that contrary to IPSPs and EPSPs, which are graded responses, remember the habanero and tahini example, action potentials are not graded. That is to say that the magnitude of the potential is not related in any way to the intensity of the stimuli that would elicit them. Action potentials just are. They're either on or off. And this is what's known as the all or none law or all or none response. Your neurons are either engaging in an action potential or they're not. In order for us to determine whether the cell is going to be on, we have to look and understand the threshold of excitation. And this is the level that is necessary in order for an action potential to be generated. You see, if the cell is at -70 and an EPSP barely makes it to a little bit less negative to -68 or -67, that would not be enough to generate an action potential. In order for us to generate an action potential from several EPSPs, it would require that we bring the level to approximately -65 millivolts. Once we reach -65 millivolts, there is now a point, that's what we call the threshold of excitation, and at that point the cell would have an action potential. Again, in order for this to occur, a summation of EPSPs would be required. Here we can appreciate a quick recap of the things we've talked about in previous slides about EPSPs and IPSPs. Remember that these are graded responses, meaning that the amplitude is proportional to the intensity of what's eliciting them. It is also important for you to note that EPSPs and IPSPs travel passively from their site of origination. And that is to say that once we stimulate them in some way, let's say that at this point you felt a mosquito in your arm, as we saw in the previous example, and then it barely made you a little bit aware of that. Once made you aware of that, it actually just cruises on. It doesn't have a constant triggering at several points along the axonal membrane, meaning that once it just goes up, it basically cruises back down and it goes down. In order for us to reach a level of threshold of excitation, you would need another EPSP here and perhaps another one so we could reach the -65 desired threshold of excitation. An IPSP is demonstrated here where perhaps rather than feeling anything, you would hyperpolarize, meaning you would make the cell even more negative, and that would be temporarily and eventually just goes back down. Perhaps you have another one thereafter and it goes back down. But the bottom one here, you could see the magnitude of action potential. Compare this to this EPSP. The EPSP is rather minimal. Here you see a summation of EPSPs that would have allowed for the cell to reach the threshold of excitation, -65, and from there, collectively, these would generate an action potential, which would allow the cell to go from -70 to +50. Here you see that right after that, it would go back down very, very fast, and it would temporarily be hyperpolarized, meaning it would not be able to fire here at all, and it'd be difficult for it to fire here. Then after that, it stabilizes itself, and it's ready to fire again if necessary. One last point of this slide is that EPSPs and IPSPs are decremental, and that is that they get smaller as they travel. Here you could see an example of that, where as they go up, it starts getting smaller and smaller and smaller, and eventually goes back down. Same thing for IPSPs. You'd see that there. In effect, each multipolar neuron adds together all the graded excitatory and inhibitory postsynaptic potentials reaching its axon, and then it decides on its own to fire or not fire on the basis of their sum. If you have a lot of PSPs that are able to generate or reach the point of no return, that threshold of excitation, negative 65 millivolts, then it would then decide to fire, and then you'd have an action potential. If it doesn't, then it may simply ignore, and you would not have a response. Neurons are the ones that integrate incoming signals in two ways. And this is what we look at: the spatial summation, which would be over space, or temporal summation, which would be over time. Please note that the integration basically consists of adding or combining these number of individual signals into one overall signal. Here we can perceive visually three possible combinations of spatial summation relating to space, and that's on your left side of the screen. On the right, we have the two possible combinations of temporal summation, and that we're referring to time. Starting with the left at this spatial summation, please note that each of these right here, A, B, C, and D, would be buttons of a presynaptic neuron, a presynaptic cell. This here would be our postsynaptic neuron receiving the impulse. In between, we would see the synapse, the space between. Notice here that when we look at two simultaneous PSPs, the sum would produce an even larger PSP. So if we just get a stimulation from A, it barely moves from negative 70 to about maybe negative 69 or negative 68. B by itself does the same thing, from negative 70 to about negative 68. But if we combine the two, A plus B, then it generates a larger PSP. Notice it did not reach the threshold of excitation, so it did not result in an action potential. Here's another example looking at IPSPs, inhibitory. Remember, inhibitory means it decreases the likelihood of a neuron firing. Well, this one here says that we're getting closer to action potential. These here actually mean we're getting farther away from action potential. So the C stimulation could perhaps be an IPSP. Here's another one with D stimulation with a IPSP, and combined it would bring about a greater IPSP, making the cell hyperpolarized, making it harder for the cell to fire. And when you have a combination, a simultaneous combination of IPSP and EPSP, is that they cancel each other out. So you have A, which is an EPSP, C, which is an IPSP, but because they both just acted in different directions, it basically cancels out any response. On the right, we see temporal summation. Here you see the terminal button again, another terminal button, and you have the postsynaptic neuron here. The A would represent an excitatory synapse, whereas the B would be an inhibitory synapse. Here's what happens when two PSPs elicit on rapid succession from each other, and what occurs. You see, if I have an A, which is an excitatory, and then shortly thereafter I have another one, you see, this gave the cell enough time to get back down to its original resting state of negative 70. You hit it with another PSP, and it goes back down again. If you have them a little bit faster or a little bit closer to each other, then a more rapid form would not allow the cell to go back down to negative 70. Instead, it would, right before it reaches down, you have another one, and perhaps you'd hit it with another one, and now we reach the threshold of excitation. At the bottom, we have the same thing here. You have two IPSPs, and if there's enough time between them, then it goes back to its negative 70. But if it is within rapid succession from each other, then you would see that there is a more intense hyperpolarization of the cell.